Okay, let's just dive right into this explainer, because we're looking at a mystery that literally confuses frequent flyers all over the world. We're talking about why a flight from Los Angeles to Tokyo completely, and I mean entirely, avoids the middle of the Pacific Ocean. Seriously, if you've ever stared at that little in-flight map on a long journey, you've probably asked yourself, why on earth is my plane flying this massive, exaggerated curve way up towards the Arctic instead of just, flying in a straight line across the water?
I mean, it really kind of looks like planes are just terrified of the open ocean, right? But to understand why these aircraft seem to hug the coasts of Alaska and Canada instead of just shooting straight across the Pacific, we have to look at route planning, like it's a highly complex video game. To get that absolute perfect flight path, planners have to beat three distinct levels of a puzzle. And the very first boss they have to defeat? Well, it's our own human perception.
Because the first hurdle is actually a geographical illusion that, let's be honest, we've all fallen for since elementary school. Flat, two-dimensional maps. The simple fact is, the Earth is a sphere, and trying to flatten it out is literally impossible without breaking something. Imagine a stubbornly determined pilot taking a giant mallet and trying to smash a physical globe perfectly flat like a pancake. What happens? It just violently pops, right? You just cannot perfectly represent a 3D sphere on a flat 2D piece of paper, and that inherent flaw completely warps how we understand distance.
Now, to try and solve this flattening problem, a Dutch geographer named Gerardus Mercator came up with the Mercator projection way back in 1569. And don't get me wrong, it was incredibly useful for early sailors because it kept compass bearings accurate, basically turning the globe into this neat, easy-to-read rectangle. But, and this is a massive but, there is a huge catch here. While a straight line on a Mercator map looks like it goes right through the middle of the ocean, the map is essentially lying to us. By stretching the poles out to make that perfect rectangle, it highly distorts the actual shortest distances across our planet.
So, this brings us to a huge, fundamental difference in how we navigate. There are really two entirely different ways to get from point A to point B. The first is called a rhumb line. This is a route where you maintain one constant compass direction, and sure, it looks beautifully straight on a flat map. But since the Earth is curved, if you actually follow a constant compass heading, you end up flying a longer, spiraling path over the actual ground. The second method, though, is the Great Circle route. This one doesn't keep a constant compass heading, but it actually represents the true, mathematically shortest distance over the curved surface of the Earth. And what's really fascinating here is the visual definition of a great circle. It's a line that literally slices the globe exactly in half. Now, the equator is the only great circle among the latitudes, but you can draw a great circle between any 2 points on the planet. Try this. Take a piece of string on a physical globe and pull it tight between LA and Tokyo. That string is going to naturally find the shortest path. And guess what? That path does not cut across the middle of the Pacific. It naturally curves way up toward the North Pole and then comes back down. Flying this curved Great Circle route actually saves airlines thousands of miles, which cuts down massive amounts of travel time and, of course, fuel.
Okay, so the math proves that the curve is actually the fastest and shortest path. But let's move on to level 2 and ask a much more practical and honestly slightly terrifying question. What happens if an engine fails, or there's a serious medical emergency right in the middle of a vast, empty ocean? Because the shortest mathematical distance absolutely doesn't mean much if you're stranded thousands of miles away from the nearest runway.
And this is exactly where strict aviation safety protocols step in. Aviation authorities enforce a completely non-negotiable rule known as ETOPS. That stands for Extended Range Twin Engine Operations Performance Standards. It's a mouthful, I know. But simply put, this rule dictates exactly how far a twin-engine plane is legally allowed to fly from an emergency diversion airport at any given second during its flight.
For the vast majority of modern commercial twin-engine planes, their ETOPS rating requires them to be within a 2 to 3 hour flying window of a suitable runway at all times. No exceptions. Now think about the middle of the Pacific Ocean. That is a whole lot of water and virtually nowhere to land. Flying straight through the dead center of the Pacific turns the journey into this massive danger zone where reaching an airport in under 3 hours is mathematically impossible. But by following this ETOPS rule, anytime you're flying across the ocean, you are guaranteed to be within that 3-hour lifeline. And honestly, this brilliantly illustrates why that northern curve is so absolutely crucial, way beyond just saving on distance. By hugging the landmasses of Canada, Alaska, Russia, and Japan, airlines are constructing this continuous, life-saving safety net. If a warning light suddenly flashes on the dashboard while they're flying this northern arc, the pilot knows they are always within a safe, easily reachable distance of a diversion airport.
It's this perfect marriage of mathematical efficiency and rock-solid safety.
All right, level 3, the invisible rivers. Now it's time to face the final boss of route planning.
To really understand how wind impacts a massive airliner, think about this brilliant analogy they use in naval aviation. Imagine a plane flying inside a giant balloon. Now the aircraft can fly at a perfectly steady, predictable speed inside that balloon. That's its airspeed. But if the balloon itself is being blown backward by a massive gust of wind, the plane's actual speed over the ground drops dramatically. It's the combination of the aircraft's speed plus the moving air mass it sits inside that actually determines how fast you get to your destination.
Which brings us to the jet streams. These are massive, high-altitude rivers of wind blowing from west to east right around the globe, and they can reach absolutely incredible speeds of up to 200 miles per hour. This creates a really fascinating dynamic for pilots. If you fly straight west from North America to Asia, you are fighting a massive, fuel-draining headwind the entire time. It's literally like swimming upstream. Your ground speed tanks, and you burn significantly more fuel. And we're not just talking about adding a few minutes to your flight. We're talking about millions of dollars in extra fuel costs, which, you guessed it, ultimately hits your ticket price. Conversely, though, flying east gives you a massive tailwind.
Because of these invisible sky rivers, the route you take going to Asia is almost never the exact same route you take coming back. To avoid that brutal 200-mile-per-hour headwind on the way out to Tokyo, pilots will actually often fly even further north than the Great Circle math dictates, just to navigate around the absolute worst of that jet stream. But on the return trip back to North America, they deliberately alter their route to fly a bit further south over the ocean. Why? So they can intentionally get caught in that massive tailwind, effectively grabbing a free speed boost that slashes their flight time and saves an incredible amount of fuel.
So, the really crucial takeaway here is that drawing a flight path is never just taking a straight edge to a map. A route planner has this extensive checklist they have to balance perfectly. First, they calculate the Great Circle math to find the absolute shortest spherical distance. Next, they overlay those ETOPS safety limits to make sure the plane is never more than a couple of hours from a safe runway. And finally, they tweak and adapt that path to either ride or dodge those ferocious jet stream winds. It is just this beautifully complex combination of spherical geometry, life-saving safety protocols, and meteorology coming together to create the absolute perfect flight path.
So, the next time you're thousands of feet up in the air, maybe sipping a ginger ale and staring at that glowing in-flight map on the seatback screen, I want to leave you with this to ponder. Is the simplest, straightest route you see on a piece of paper actually the smartest path in a three-dimensional, wildly dynamic world? Turns out, those big, beautiful arcs you see aren't detours at all. They're literally the smartest shortcuts we have.